ladies and gentlemen, my name is Nick Dalaku, and I like to think about myself as a hands-on physicist for our institution. Last year, Tom Savaggio, grade 6 science teacher for Maple Avenue School in Niagara Falls, New York, came to me and asked about a field trip at our museum. It was music to my ears. We prepared for such an action, and we came up with a successful event. I called it physics class at the museum. I learned that grade 6 has a well-established curriculum. They have to know about waves and sounds and light and all the properties and attributes it was in that curriculum for those kids. We repeated this event this year, and another 2 schools participated, and it was a successful event again. This video is about part 1 of our presentation, and it is about wave and sounds. As you could have been guessed, the presentation is done on old scientific instruments, on old philosophical apparatus, and I enjoy tremendously doing it. Everything here, I don't know if you observed already, it's we're trying to use only very old apparatus, demonstration apparatus. Why? Because first, the old ones are much better built than the new one, and because in the old one, the functionality, what they want to show, is very transparent. You can feel almost immediately what they made for. Today, everything is thrown in a piece of plastic.
That's an official blackboard too, by the way. That's what we used to use teaching years ago. Blackboard, slate, and chalk.
I see in your book that this formula, that it's just given the lambda equal speed of the wave multiplied by time, or time is 1 over frequency, doesn't matter. It's just given there without any explanation. I think we can feel, we can invent this formula. How come? If you drive, if you go in your car, or your parents' car, and you have to think about when you arrive at destination, can you do this judgment in your brain?
Yeah.
How? How do you do that?
Distance times time.
But as simple as that, but do you feel it? Sure. So if you have speed, that means that you travel as much as that in each unit of time. That's how we define speed, yeah? How many miles per hour, yeah? Now, if you know how many miles per hour, and you know how many miles is between one town and another, it's very easy to understand how many hours will be to get from here to there. You divide the space by the speed, and you get the time. And based on that very simple thinking, you invent this formula that lambda equals speed multiplied by that t, which is the period, the inverse of frequency. The period is the time in which the wave goes from one maximum to the next maximum, or from 2 consecutive similar points. Now, to go to the really subject of our presentation here, how we feel experimentally what sound it is. Maybe one of the best examples is this one, which is the so-called neutral cradle. It can be used to demonstrate all the laws of mechanics. We are going to use now to demonstrate the mechanism of wave propagation. So we have here 5 stainless steel balls. It could be 100 or 1000. We take one from the equilibrium, and then we let it go. Nothing happened from here to here. Only the first ball is taken from equilibrium and it's transferring its energy to the end of the row. What's happening? We give this one potential energy because take out of equilibrium, this potential energy becomes speed, kinetic energy when it's down here. Then elastically interact with the next ball, and that interaction is compression, and so on. The things it's transmitted as far as it can go. So we have a disturbance, and the propagation of this disturbance is called wave. So that's the definition of the wave. A disturbance which propagates in space with certain speed, it's a wave.
So it's good to see that transfer of energy. And you talked about potential energy turning into kinetic energy, and then it's being also transferred from one to the other.
Let's go to sound now. Sound has the same mechanism. But who are the balls in the case of sound? Can you tell me? We said here we have 5 balls. But if sounds, it's the same mechanism. We are the balls. Pardon me? Oh yeah, there are a lot of them. Which are the balls? Are the molecules in the air. Okay, now we have here an example which illustrates perfectly that one. So in the air there's unbelievable amount, it's the Avogadro number. It's a huge, billions of molecules per each unit of volume. And this apparatus will simulate what's going on. Now, what's amazing is that in air, the molecules move much more faster than in here. And here is very noisy, and you don't hear this noise in air. But the movement of the molecules in air is much more intense than here. Now I guess you can build in your mind the model. You have our vocal cords, which vibrate. By doing that, it makes the molecules in air in front of, in the path of that cord to vibrate too. And we're going to be expanding, radiated, how we call, and compressed. And that thing is transmitted as far as the sound reach. Now you know about frequency, and we talk about the T period. Frequency is it's how many oscillations per second, and that's a good example. We have 4 wheels. This one has many teeth. This one has less teeth. Teeth.
Yeah.
Now, what we're going to have which, if I put this one against them, we're going to produce a sound. Which sound we're going to have higher pitch? Can you tell me?
The one with the more wheels.
As simple as that, bravo. It's simple, but just this type of understanding is so, excuse me to use a coarse word, but it's so damn important, that simple understanding. Now, let's see if I'm right. So this is high pitch. So you see the difference, yeah? Now to go to a little bit nicer, more melodic sounds, let's go to, you recognize those devices, do you? Huh?
Are music people? What are those?
Music people, what is that?
Tuning fork?
It's a tuning fork. Now, let's see what we got here from that tuning fork. it's a sound very clear. And not only that, it is a C note, and it has the frequency of 256 hertz. No more, no less, 256 hertz. It's 256 oscillation per second. Remember that. I guess 256, that C note, it's an important in music, because that's everybody, the music teacher, we're gonna try to hear that, and then we're gonna say do, and that what he says with his mouth has to match what he heard from. Now, somebody played with this one. This is the same thing as this one. However, it has those waves here which gives us the ability to change the frequency a little bit. Will be around 256, and let's see if I'm right. Is this note the same as this one? Who can tell me?
No, it is not, because that is a higher pitch, the one without the weights.
Who's telling you that? Your ear?
Yeah.
You might be right. No, you're not right. I'm not, because I trust my ears more than yours, but because it's written to be 256, and that's at the position which has to be 256. Oops.
Okay, maybe not.
You stand corrected. I agree with you.
Yeah.
Now, one thing here you can learn a little bit more. There's in a lake, if you throw a stone into the lake, or you throw two stones and those start interfering with each other, then you're going to see the interference, the superposition is called, of one wave with another.
So combining of the two.
Combining of the
Blending.
two, when one of the wave is maximum and the other one is exactly on top of it, you have amplified the sound. The sound will be adding up, one amplitude plus the other. When somehow it's inverse, it's subtracting and you hear nothing. Now, if they are the same frequency, sorry. Now, that's a imitative complication right now. What was that funny noise? What we obtained there? Can somebody tell me? You girls. Why there's noise? It's so different than this one. What it represents?
Because of the different things you're hitting it with, one's south, one's rubber.
What they are? They're just
Noise frequency?
noise, or they're different sound. It's an harmonic of the first one. This side, it's harder, the rubber, and it produces an harmonic. So that was an harmonic, maybe 3/4. So you have 256, a do here, but you have a do there, which it's just
It's
an
a lower
harmonic.
frequency.
It's a multiple of 256. So one, you can see the beats, yeah? You can see as the surface of the lake just combining one wave with another. Okay, just to go fast to it, another way of producing this type of sound, that's against, it's a do too, it's with a pipe. Now again, here you can change the pitch as you do here like that, by changing the length of the color. So there are many ways, with the strings, so many ways to produce different sound. Now, this is a siren. It has a volume over here, and it has some holes into the top of that volume. And on top of it, it has a cover which you can rotate. This one has the same number of holes too, but they're sort of in an angle. So this is the cover, this is the volume, this is the pressure, the tank with the compressed air. Now it will be pretty noisy, but I think it's worth it. You see that start moving? Now I closed, it's moving fast, but because air doesn't go through, you hear nothing. If air goes through, it is that interaction, it is this type of pattern. Only one thing which I forgot to show you, and then we get out of here and we try to, I'm trying to show you in the lab the things which we still has to be seen. Now,
Kevin, you're in the shot.
so what I'm trying to do here, you tell me. I'm trying to show you that the sound needs a medium to propagate. The electromagnetic wave, the light, they go very well through the vacuum, but the sound needs air. So that's a manometer. It shows the pressure in this thing. And check it out what happens if I increase the pressure, if I increase the vacuum.
What are you noticing?
It's getting quieter.
Okay, why do you think it's getting quieter? Okay, she's thinking there's more air in there.
No, it's vacuum. We're taking the air away. The molecules you see in the air, we suck them out. So those molecules which transfer the sound, they're less and less. Now, I perspire enough. I don't want to do that anymore. So you got the idea, yeah?
Yeah.
Less molecules to transmit the sound, then less sound is propagated.
You can watch the gauge too. As the gauge goes down, it's going to get louder and louder. So this is the vacuum I was talking about where the air is getting sucked out, and so that we can't hear the sound. As the air goes back in, the more air, the louder the sound.
I hope I didn't turn you off with my broken English and mostly with my not so robust mind as I used to have. The bottom line is it's using all antique science instrument. It's a very good thing, and this exercise is very much in sync with STEM programs to promote science and technology and engineering within the young generation.